So we're gonna do 5.4 next, and we're gonna talk about the Fundamental Theorem of Calculus. This is a big deal. Ever see that movie Step Brothers?
Yes.
Oh God! Why'd you bring that up?
Or no, it's not Step Brothers. It's Weatherman, where he goes, where Ron Burgundy goes, kind of a big deal. This is kind of a big deal, right? I always got to fit in like a Will Ferrell reference, but the Fundamental Theorem of Calculus is a big deal. Let me write it out. There's two parts to this, and this will definitely be on the test. You need to know this, need to know it, need to know it, need to know it. I can't stress it enough. So we can take f of x can represent a value. Capital F of x is really a y value. It represents a number. That number can be calculated as an area under the curve of a derivative. Okay? Now this is if f is continuous on a, b, then the function capital F is equal to the area under the curve of a derivative. And it has a derivative at every point x. So if this is true, if I take the derivative of capital F with respect to x, then I can take the derivative of this with respect to x, okay? And that equals f of x. And I'm going to do an example of that in a second. So what I'm doing is I'm taking this equation. Remember what an equation means at the root of it. It means that this is a value that equals this value. But we're representing those values in a variety of functions that are evaluated a certain way. So now if I take the derivative of the left-hand side with respect to x, then I take the derivative on the right-hand side in order to maintain the equivalency of the statement. Whatever you do on the left-hand side, you have to do on the right-hand side of the equal sign. Okay? When you take the derivative of an integral, you're undoing what you're doing. It would be like taking the antiderivative of the derivative, except we're taking the derivative of the antiderivative. So they're inverse operations. They kind of cancel each other out. So we're left with f of x. Remember, this is like f prime. Right? F of t is like f prime. So it's like you have f prime and you go backwards. But if you take the derivative of that, guess where you end up? Right where you started. So let me write that down on the board in red so you can understand what I'm saying. If I start with f prime of x, and I integrate that, I end up with f of x. Well, that's kind of what this is, right? I'm integrating my derivative. But then if I take the derivative of that, I end up right back at f prime of x. So let's try to apply this to example number one. So example number one in our textbooks wants us to evaluate two functions. So I'm going to take a look at the derivative with respect to x of negative pi to x of cosine of t dt. And so the solution to this is that if all this stuff is correct, this should be equal to cosine of x. And the reason in the notation when we say a, so let me go back because I kind of skipped over that. If this is x, where it's a variable x, whatever this variable is, that's the variable we'll end up with here. A is not a variable, it represents some constant. So the constant really doesn't matter. I mean, it does, but in this particular case, with regards to the fundamental theorem of calculus, it doesn't matter. If I were to take the integral of this, I get this. That's it, plain and simple. All right? There's a long, complicated proof of that, and if you want to, you could read it on page 294, and we'll do that for another time. Just kind of soak this in. Now, another example of this would be d dx evaluated from something to x. So the key here, and this is the function of 1 over 1 plus t squared dx. Now the textbook actually puts 0 right here, which is a constant. But again, the constant doesn't matter so much. I have the variable x here, which means, whoops, my apologies. This should say d dt, because it's a function of t. But this function is just 1 over x squared. That's it. We just have to accept that. Okay? And that's it. Now, if they plug in some value for x, then it's a different scenario. But for right now, this is part 1 of the fundamental theorem of calculus. Are there any questions?